My name is Chavez. I'm a first-year PhD student at New Mexico State University. And today I'm going to present you and share some of the work that we're doing specifically in spiking neural networks in the field of control systems engineering, particularly on the UAV or unmanned air vehicles, or AKA drones. And some of the motivation for this work is that, as we know, the premise for all of us here is that spiking neural networks are based on the function of how the mammalian brain works. And of course, this gives the premise that it is very energy and data efficient than normal artificial neural networks. And of course, in drones, it is very necessary to have energy efficient systems because we don't have anything, we don't have a constant source of power to them. And this is why in order to harness this, we need to develop these controllers and apply them into neuromorphic computational architectures. And some of the work that we've done in our research lab is we've developed some spiking neural network controllers, specifically on the limbic system, inspired control. And of course, during my master's, I also did some work on the application for a real-time platform. And the objective for this work is to develop a spiking neural network-based controller to perform spatial stabilization and trajectory tracking of an unmanned aircraft system. For this work, we used proportional derivative control laws as foundational framework. We used the neural engineering framework, or Nengo's Python API, to implement the neural controller. And we used to test the controller's effectiveness. We evaluated using the flight simulation environment, and specifically X-Plane. And in order to solve this problem, or to develop this controller or drone system, was based on the mathematical model based on Newton-Euler formalism. This takes into account all the forces acting on the drone, and based on the function of the rotors and the torques of the motors. And of course, since we are not taking, we had to reduce this model, and since we're not taking into account other external forces rather than gravity, we reduced the model so that this is our classic PD controller, where we have, as if you're familiar with control systems engineering, in here we have as inputs the location of the drone, translational velocities, and angular velocities, where inside the controller, there's some computation that happens, and after that we obtain signals that go to the rotors of the drone. And in order to translate this to a normal or spiking neural network domain, as I say, we use the neural engineering framework, which and the NEF proposes a way to transform a physical magnitude or signal into a spiking neuron finite rate. This is done through an encoding process where the vector representation or the signal is represented in a neural population, and these neural populations represent the dynamic state over time through nonlinear encoding and linear decoding. So in this case, we have an input current where it goes through some encoding. We obtain some spike trains, and then we extract the output current. And this is done through the decoding process, which translates the neural response from the neural population to the actual signal that we want to use. This is done through a mix of decoding matrix weights, through convolution operations, and synaptic filters. And this is our main work. This is kind of like a translation from the classical PD controller to a spiking neural network. This is very particular of Nengo, but in this case, we have, for example, in the circles are the neural populations, and the squares are the conventional signals. And if we compare them side to side, we can see how their resemblance from the classical PD control to the spiking one. Basically, this was like a translation from the classic one, where in order to prove that this was working and functional, we did an experiment where we integrated the spiking neural network controller to the X-plane so they can communicate. So the drone was running on the simulation environment, sending information to the controller and the controller back. In this case, for this experiment, we did a mission profile. As you can see on the image on the right, we had a takeoff, climbing to a particular position, and then we did a tracking of a figure 8 reference. And where red is the desired position and the black is the actual position. And as I said, the communication structure, we had the X-plane communicating to the computer. The computer was running the spiking neural network controller, and the spiking neural network sent information back to the physics-based flight simulator. And on the right here, we can see the actual drone flying. And as, some of the results that we got, first of all, with the Euler angles, the desired and the measure state, as you can see, the controller works. We have a small error between the desired and the actual angular Euler angles. And however, we can see how the controller has some difficulty accommodating to abrupt changes for the desired position. And this is, you can see this easily in the angular velocities. And as well, we have some orientation errors and spiking activity. And you can see how the spiking activity changes depending on the value of the angular velocity and orientation errors. And in conclusion, we demonstrated the adaptability and performance of a spiking neural network controller to autonomous flight mission. And in future directions, we will like to develop this spiking neural network controller in a neuromorphic hardware in real time, incorporating also neuromorphic sensors such as the event-based camera. And as well, I'm working on writing low-level code using NXSDK for Loihi1, which is the one that we're using because it has a small factor. And some acknowledgements here. I want to thank Dr. Garcia Carrillo and Dr. Anderson Borger, which are my advisors. They are the light of my PhD journey, and as well other colleagues, Ignacio Ruizcola and Eduardo Stier Espinosa, as well as this work was supported by the NSF and the Department of Energy and the National Council of the Mexican National Council of Science and Humanities.